All right, let's see how if it's a work now, right? Right, Olia. So I am trying to redo this, trying to make sure that when you have when I want to review, everything will be online, right? It will be on YouTube. I think the channel is Arete Institute of Science. All right. I will saving this one as electrostatics. All right, let's see how it will work out now. It worked okay, that's not for the form fives. I just want to see how it will work out for all, right? Good. Everybody hearing clearly, right? Let's do a quick review of what we did over the holidays. Just give me 1 second. You might be getting feedback. All right, let's see if I get it to work here, right? You'll get any feedback online? Like as a talk, you'll get any feedback? No? Okay. All right. Hopefully it works in there. Hopefully it works there. All right. So during the holidays, we started electrostatics, right? Remember, we finished up module 3 and we started module 1, sorry. We talked about electric field being a vector quantity, and we talked about how to get electric field strength. We also talked about how to find electric force, which is electric field strength by charge, right? We talked about it being a vector quantity and how to determine these values. We've talked about electric field lines, leaving the positive and going towards the negative. Here's an example of where you have like charges repelling and unlike charges attracting, right? You have to be able to draw your field lines, right? Here we have two parallel plates, and we said that the electric field strength is given by E is equal to Phi on D, right? We talked about uniform electric fields, and we said that the force exerted by uniform electric fields is VQ on D, right? That is by substituting this in this, okay? So we talked about electric field strength and how to work it out and so on, right? Right, then we talked about them moving in an electric field and how it's comparable to projectile motion. Then we spent a lot of time on Coulomb's law. Coulomb's law basically looked at how two charges, how these two charges separated by a distance r, how the force between these two charges, how you find their magnitude, right? And it's given by this relationship here, which is Coulomb's law, right? F is equal to the product of their charges over the square of their separation by the constant 1 on 4 pi epsilon. Epsilon is the permittivity of free space, and it's given by this value here, 8.85 by 10 to the minus 12. Then we also talked about finding the electric field strength due to a point charge. So if you have a point charge here, you want to find the electric field strength due to this charge here. Okay. And after that, we talked about electric potential, right, which is defined as the work done per unit positive charge and bringing infinity to that point, right? And we saw this relationship here. And then we did, we had the relationship here in terms of Coulomb's law. Something very important is that potential is a scalar quantity. All right. Nice. And here was a slight comparison, right? We compared everything between gravitational field and electric fields. Okay. This is what we have to focus on for unit 2. But it compares to something that you would have done in unit 1 for electric fields. So it just draws an analogy between these two here to show you how similar they are. For gravitational fields, we deal with masses. For electric fields, we deal with charges. All right. Today, we want to focus on an application now of these charges, right? This is where we talk about capacitance and so on, right? All right, so good. Most people were here who wasn't here for the holidays. Most of you were there. Savvy not here. All right, ready? So you want to talk about capacitance, right? Capacitance is basically a conductor, and it has the ability of storing charge, right? So you don't have to write everything here. We just run into this, and then we'll do some simple calculations on it, right? So the capacitance of a conductor is the charge stored on the conductor per unit potential. So capacitance is the charge stored per unit potential, right? Or per unit voltage. So capacitance is charge, which is coulombs per volt. All right. So this here could also be written as this new unit, which is farad. There's a little mistake. There's capital F. Right, so the SI unit for capacitance is farads, right? So you're making little notes, write the formula, write the SI unit, right? So make sure you have it as we move along. Make a little note. 1 farad is the capacitance of a conductor, which carries a charge of 1 coulomb per unit potential, right? So 1 farad is equal to 1 coulomb per volt, right? So capacitance is the quantity that we measure how much charge a capacitor could store. Right? So the capacitor is this device that allows us to store charge, right? And we give an example of where you will find a capacitor. You use it all the time. You use it all the time. And your phone, your battery is an example of a sort of a capacitor, right? So eventually all capacitors consist of a pair of conducting plates separated by an insulator called a dielectric. We'll be focusing on dielectric looking like here. So you have 2 parallel plates, and in the middle you have a dielectric, right? That dielectric is air. Okay. right? The circuit symbol for capacitance, what it's missing, right? That's the circuit symbol for capacitance, right? Right, and we looked at the definition of thing already. Right, one thing you will notice that is that 1 farad, right? 1 farad is an extremely, extremely large capacitance, right? And she spelled it wrong. Farad is F-A-R-A-D, right? So 1 farad, right? 1 farad is an extremely large capacitance. So really and truly, the capacitors that you'll be seeing, those values are in the order of millifarads and more so microfarads, right? Let me just show you an image of a capacitor, right? Do me a favor now. Go on the live and just I want to see how this is looking. Just go on YouTube. RIT Institute of Science. Right, this here is kind of what your capacitance will look like, and on the side of it, you will see your values. Right, it will look something like this. And on the side, you will see your values, right? This one looking like a 160 microfarad. It upside down. This one here is a 2,200 microfarads. How it looking? Let me see. Just seeing the images on the live. On the live, nice. Okay, so this is what your capacitance will look like, right? If you use a capacitor in the lab, it will look like that. And these generally are your values, right? Like 2,200 microfarads, something. You'll see it online, right? Victoria, you'll see it there? Yeah, okay. All right, so that's kind of what your capacitor will look like, right? Watch this quick little simulation of it there. Right, it's just showing you how the capacitor, how it basically stores the charge, right? Tell me if you're not seeing it, right? You all seen everything there? Yeah, okay, nice. All right, so let's turn it on. Right, what you will notice, let's go back to 0. What you will notice is that, show you all the values, right? What you will notice is that when the voltage is 0, there is nothing on the capacitor. You see anything at all? No negative or no positive charge. But after a while, this is not time related, right? But after a while, what should happen in there? The top plate kind of becomes positive and the bottom plate becomes negative. You'll see that? So what that means is that between here, charge is being stored because the potential is building up. You'll see that? If I were to increase it further, what you reckon is happening? Voltage becoming larger. Yeah, you'll see that? Right? It becomes larger and larger. Look at the value for capacitance. The value for capacitance going up a little bit, right? Sorry, for charge on the place going up a little bit. Okay, what would happen if I flip it around? So the negative, the electrons switch sides. Recognize that? Right? What will happen? What will happen? You'll see now online, right? So if I increase the voltage, the capacitance value is 0.3 picofarads, right? What will happen now if I were to increase the separation? So I increasing the separation a little bit. What you recognize about the capacitance? It's going up or down? It's going down again, smaller. So by separating the plates, it's affecting the capacitance. That's okay? So bringing it back down a little bit. I keep it at about 3. Look at the area of the plate now. I'm going to make the area of the plate larger. What you all recognize? Capacitance increasing, right? Yeah, Brian, you're looking at this value up here, right? That value going up, right? See that? So we have a larger capacitor there. So what are two factors affecting the? What are 3 factors affecting the capacitance? 3 factors are what? Voltage, separation of the plates, and area of the plates. Yeah? Right. What's the ability that the capacitor has, right? When here is 0, there is nothing. If I were to break the circuit and switch it here, bulb lighting, bulb not lighting. But watch this here. If I were to build up a little charge and switch it, bulb starts to light. Sadly, what happening? All the charge is being used, right? All the charge is being used until the capacitance drops, the charge up to 0. Are you okay with that? Online? You're okay with the principle there of the capacitor? How it works? Okay then. You okay with that there? So Karen. So Karen, suppose I wanted to I want to turn back on the bulb. What I could do? I want to turn back on the bulb there. Why are we not seeing it? Karen, you there? Carol. Carol. Carry up the voltage. Look at the circuit properly, yeah? I carry up the voltage, but nothing happened. So you're close there, but I do something else as well. Connect the dielectric. Well, yeah, not the dielectric, but connect the capacitor. So I connect the capacitor, and I have one little question, right? When I turn on the voltage, why it is here negative? Anybody can guess? Victoria? Or looking for a little guess. Why you think they became negative? Victoria, any guess there? Because, right? Ramos correct? Right, so here's what Ramos said. Ramos said that this is the negative side. So the negative side will possess a set of electrons, right? So when I connect this circuit, the electrons will flow here. and then the electrons will stay on this plate, right? When the electrons start to build up on this plate here, because here negative, it will push all the electrons that may be existing on this plate here, right? Then here becomes positive because all the electrons on that plate leave, right? Brian, you okay with that? You okay with that? So the electrons from here move through the circuit and settles on the bottom plate. Now the bottom plate becomes negative. What I will do is that I'll push all the electrons from on top here back to the opposite side of the battery. Because it will kind of like create a circuit now, create a kind of flow. And here becomes negative and here builds up to positive. That's okay? What do you think will happen? And look at the values, right? What do you think will happen if I keep increasing this value for voltage? If I keep increasing this value for voltage, you see that the total charge being stored is larger, right? Right? And of course, if I switch it back here, the bulb going on, the bulb is going to light, going to use all the electrical energy. And as it uses all the electrical energy, the capacitor will lose its charge, right? See that? Right, so that's basically how the capacitor works. All right, let's go back into the theory side of things now. Let's go back, way back. Emil, you okay with that? Emil, you okay there, right, Emil? Thing real delayed, boy. Emil, you there? Right, Victoria, follow that, right? How the capacitor kind of works now. Yeah. Okay, so we have the gravitational, we have the capacitor. We said that capacitors is a device used to store electric. Gave you the symbol. Capacitance of a capacitor is defined as a charge stored in either plate per unit potential. Capacitance, I gave you the formula. I told you 1 farad is quite a large value, right? So generally, as I showed you in the example, is that your capacitors will generally be along the microfarad region, or even like in our calculation, a pico, right? The capacitance of a parallel plate capacitor is given by this little formula here. So yes, we have capacitance is equal to Q1V, but as I showed you in that simulation, capacitance is dependent on the dielectric, right? The dielectric, the permittivity of the dielectric, the area of the plates, and inversely to the separation. I remember that? Yeah? No? All right, so this is the next way to find capacitance. All right, before we do charging and discharging, let's try a quick example. As I said, the value that we're going to use, is the permittivity of free space. Let's make a note, 8.85 by 10 to the minus 12. Right, that's the value for permittivity that we will use. Ready? Let's do a little example to just make sure we understand. how to manipulate these little formulas here, right? So here's what I'm giving you. I'm going to give you two parallel plates, right? Separated by a distance of 5 millimeters, and the area of each plate, the area here of the plate is 2 meters squared. Right, in between here, dielectric is the same value I give you. And the potential difference, if I connect a voltmeter here and here, the potential difference is 1 by 10 to the 4 volts. Right, so part one, let's see if we could find the capacitance. How are we doing that? Yeah, any ideas? I just stick in two little, let me just add a few more. I just stick in a few formulas here that I might need, right? Which formula are we using here, Darren? How are we going to find capacitance here? Right, correct, Victoria, he's using his second formula. So the reason we're using the second formula is because we don't really have, we can't find, we don't know Q as yet. Right, I just want to number the formula, so you'll tell me which one to use. So you're using the second formula. Right, we can't use the first formula because we don't know Q. So the capacitance is equal to epsilon A on D. Work it out, tell me what you got. Remember to convert to meters, huh? How much you all got there? Yeah, good. I got the same thing, 3.54. 3.54 by 10 to the minus 9 farads. Nice, good job. Good. Something else to ask now. So you found the capacitance. Could you find charge? Could you find the charge on each plate? Right. Okay, then which formula I think you'll use to find the charge on each plate? Correct, Victoria. Okay, then which one I think you'll use then? Fourth one to find charge. No, remember charge with Q, right? Remember charge with Q. So which formula there has Q in it? Correct, the first one. Right, nice. Says in the first one. Q will be equal to C by V. Work it out quick. So that's 3.54 by 10 to the minus 9. And the voltage is 1 by 10 to the 4. Yeah? Done? You okay with that? Work it out, boy, again. $3.54 again. So you'll get 3.54 by 10 to the minus 5. Last one. I want to find the electric force. I want to find the electric force that this will exert. How again the electric force? Which formulas are using here, Bradley? Yeah, Bradley. Which formula or formula here that are we going to use? Right, very good, Darren. Bradley said 4 alone, 4 alone. Remember, you want to get electric force. So yes, they're using 4. And which one? Yep, 4 and 3. Oh, yep, try it fast and what you get for electric force. I remember I also gave you a version combining both of them, right? Right, message answers. Want to finish? I have one so far from Dylan. Dylan and Ramos so far. So you find the electric field strength first, and then you could find F. Much again. What do you have? Calculator. Nice. Karen, what you got? Emil, you there? All right, let's see what you got. So I said F is equal to EQ, E is equal to V on D. So you plug in your potential, 1 by 10 to the 4. 1 by 10 to the 4. Q is 3.54 by 10 to the minus 5. And divided by D, which is 0.005. Right, and from what we see, and most people got 70.8. 70.8 newtons. Right, good job, Karen. Good job, Bradley. Immediately finish it. Victoria, good. Ramos, Dylan, good. All right, nice. So that's a little intro into capacitance and using these different versions, right? Just giving you one more to try here for me. Well, sorry, 2 more to try here for me. Sorry, 3. 3 quick questions before we move on to capacitance in series and parallel and things. Try that, please. Write down the quantities you have, look at the formula and you're done. Won't take you long. Micro is how much? 10 to the what? Micro is 10 to the what? 10 to the minus 6, right? Good. Go ahead. Try these 3 here and let's correct them. Right, Brian, help me the first one here, number one. We're used to the first one. C is equal to? Huh? Sorry? 5 times 12. All right, tell me the formula you use. C is equal to what? Capacitances? What the formula you use? What's the formula you use to find charge? Right, so C is Q1V. So Q is what? C by V? Yeah. So C is what? Which is how much? That's 5 micro. So that's 5 by micro is 10 to the minus 6. So it's 5 by 10 to the minus 6 by 12, right? Which is 60 by 10 to the micro, 10 to the minus 6. Make a mistake there, right? So that'll be 60 by 10 to the minus 6. Or we could, if you want, you could say 60 microcoulombs, right? First one was easy. Number two, they gave you a constant current. So they gave you the current, which is 2 by 10 to the minus 6 amperes. And they gave you the capacity, or time, sorry, 20 seconds, right? How we get Q? Q is equal to what, Cheyenne? Cheyenne there? Right, good. Q is equal to I by T. So that's T, sorry, 2 by 10 to the minus 6 by 20. So that's 40 by 10 to the minus 6 coulombs, right? If the voltage is 20, what's the capacitance? We're using C is what? Q1V, right? Q1V, so that'll be 40 by 10 to the minus 6 over 20. So that'll give us what? 2 by 10 to the minus 6 farads. Yeah, nice and easy, right? Just to give us a little appreciation of these little things. A 20 microfarad capacitor is charged by a constant current. The capacitor is initially uncharged. How long will it take for the potential difference to reach 30? So the one potential difference, right? Potential difference is what? What's the version of the formula that we're going to use here? Huh? Number 3. I can't remember the numbers now, right? Number 3. But we have capacitance, we have the voltage you want to reach, and we have current. They want to find time. Yes, time they want. Yeah, I know, I realize. They ask how long, time. Right, so you use Q as IT and work it out. Nice. So you're using Q is equal to, like the first one we did, Q is equal to C by V. We know what C is. We know what C is. And we can solve for Q and then find for T. So Q is equal to IT, which is equal to CV. So I is equal to CV all over T. Right, C is the capacitance, 20 by 10 to the minus 6. Huh? So C is 20 by 10 to the minus 6, V is 30, and I is 10 by 10 to the minus 3. Do a little quick maths there. We will get 60 by 10 to the negative 3 seconds. Anybody got up? Yeah. 60 by 10 to the negative 3 seconds. Wait, Dylan have something different. Yeah, Dylan, let's check back your last value there now. All the others look correct. Okay, so good. So basically, we have a little idea there. Now let's jump into the charging and discharging of a capacitor. Next week I won't be here, right? Next week most likely is online. There's a chance I might miss Friday. I'll message before. But I'll already know on Friday, so I'll message on. Good. So nice. So we have a little idea of this. Let's move on. Oh, I can share a link at the video as well for this class. Huh? Yeah. You can do that. And yeah, you share a link. And so after I do the live and stuff, I can share back a link for the live, right? Anyway, while it's going, you return subscribe. All right, good. Let's talk about we kind of did this in the little simulation, but let's go through it again. You'll need a little diagram, right? We're going to talk about charging and all the graphs for charging and the graphs for discharging of a capacitor. Let's give me 1 second. I have to draw this back here. All right. I just want to make sure I give everybody the correct labeling. So this diagram here, what this diagram here kind of shows us, it shows us how a capacitor has the ability to charge and to discharge, right? I know this space is a little small, but we want to pay attention to how current behaving over time, how charge behaving over time, and where can I squeeze in voltage? I'm gonna make charge a little bit smaller. So I just want you to kind of add in the parts that are drew in there, right? If you didn't print the handout or anything, just add this to your notes, right? We're looking at charging of a capacitor, how current, voltage, and charge varies with time, right? So we have a little two-way switch here. The switch could go from A, the switch could move from there, and it could go to B. Okay? Kind of what we did in this simulation. Actually, exactly what we did in this simulation. We're just going to take a look at the graph something now. Come on, ready? Just catch leave the axes open, right? Q for Q, V, and I. And as we explain, we're going to run through how it will look. The first note here is on charging of a capacitor. Right, so you have a capacitor, you have a battery, you have a resistor, and you have a two-way switch. All right, ready? Join yourself. All right, so let's go. So we'll pay attention to how current, voltage, and charge during the duration of the charging, right? How they all behave. So the two-way switch is moved to A. So I'm moving the switch and the switch at A. Initially, current in the ammeter is positive. So there's an ammeter here, and that current reading is a maximum. So what that means is that current starting here at a value, current starting up here at a value I naught. Are you okay with that? And it strictly decreases to 0. So current appears to be dropping until it reaches 0. To be honest, it doesn't reach 0. Reaches close to 0, very, very close. So it decreases. That's supposed to be a constant. That's my iPad kind of cracked there, so I have a little thing there. I'm gonna just try one more time, see if I get a little bit smoother. It's kind of like an exponent curve. So it comes close to 0. So that's the way current over time will behave for a capacitor. That's okay? Let's do the explanation. Electrons flow from a negative terminal, so electrons move in here, right? And electrons flow from the negative of the supply to the plate Y, making it negative. So the plate Y becomes negative. At the same rate, electrons have electrons leave plate X. So electrons leave in here now. And towards the positive, making plate X positive. So now we have a potential building up. So what's the initial potential? What do you think is the initial potential? 0 or maximum value? 0. So the potential started at 0 and now it's building up, right? So that graph starts at 0. As charge accumulates, so I have a little question. What will happen there to charge now? Is charge starting at 0 or at maximum? Charge. As charge accumulates means that it had no charge, right? Remember the capacitor empty. So the charge starting at 0 there. That's okay? So the voltage and the charge looking the same. Right? They both start at 0. Yeah? So as charge accumulates on the plates, the point across the plates, the potential across the plates increases because Q and V proportional. So it means that V increasing, Q increasing. They increase to a, this thing real bad, but that's it. Oh, right, guys, she can understand my handwriting. So they increase to a point of the capacitor, opposes the EMF. So basically, the charge will increase until it opposes the EMF and therefore reduces the rate of current flow. So what happening here is that across here, potential getting larger. And because the potential getting larger, it's stopping current from flowing. So the current decreasing. That's why the current behaving like that, right? The current starting to decrease as the potential increases. Charge continues to accumulate on the capacitor with the point across the plate becomes equal to the EMF. So you see this here? When this EMF equal to this voltage, no more current will flow and the charge has reached a maximum. So this will go up to a maximum, this will go up to a maximum and stop. So that's the way the graphs will look. So no more electrons will flow when the PD across the plates is equal to the EMF of the supply. That point is really PD. I will edit this and send this back for you, right? And also she type it up back. So the potential difference across the plates equal to the EMF and current stop flowing. Okay? So if you look at the graph of current starts from a maximum and it decreases, right? Charge starts from 0 and increases to some maximum value called Q naught. Voltage increases to a maximum value V naught. So here we have the graphs of charging for a capacitor. Are you okay with that, Dylan? Are you okay with that? Yeah, Bradley, you okay with that? All right, so to your graph, you have to learn a little formula, right? There's also a formula that you need to learn, right? So the formula here for charging, I'm writing it in black, I is equal to I naught E to the minus, I had a rub of that. Anyway, to the minus T over RC. Right? Is he writing in black? For charging is Q is equal to Q naught by 1 minus E to the minus T on RC. And this one is V is equal to V naught by 1 minus E to the minus T on RC. T is time, R is resistance, C is capacitance. Let's see if we can see it a little better here. Right? Just remember, T is time, R is resistance, and C is capacitance. Later on, we will learn about RC, which is the time constant. So everything you see in here has to do with charging. That's the charging of the capacitor. Then we're going to move it to B now and talk about discharging. Adding this, it have a space in the handout for you to add it in. Everybody writing online? Anybody writing? No. Let's try discharging now. So we're moving it now from that one there. We're moving it now from A to B. Right? Let's see if we could figure out what the graphs will look like. Last thing are we done, right? Last thing are we done? Well, Victoria going already. Last thing. Karen, you there still? Of course, all right, nice. Last thing, Karen, and we done. All right? We just want to take a look at discharging. Right? Discharging and we finish. So once the capacitor is fully charged, the two-way switch is now moved to B. Initially, the current is at a maximum and then slowly decreases to 0. So the graph for the current looks like this. And we know the formula already. I is equal to I naught E to the minus T on RC. That's okay? Brian, you okay with that? And here's why. The electrons flow from Y to X. This reduces the negative charges on Y and the positive charges on X. Initially, the charge on the plate is a maximum. So you will notice that it starts at Q naught. And the point, that's not point, that's PD. And the PD across the plate is also a maximum. So it's a little bit different now. When it discharging, it's starting at Q naught and V naught respectively. And it decreases until it comes close to 0. Right? So as electrons move, the electrons moving from Y to X, the potential will drop. As the potential will drop, the charge will also drop. And the graphs look like that. And your formulas look like this. Q is equal to Q naught E to the minus T on RC here. V is equal to V naught E to the minus T on RC. Everything you see in there is discharging. All right. Sketchy graphs, write down the formula. Okay, then, you okay with this? All right, so what we're going to do next day, I want you to watch over this little part of the video, right? And we're going to start from right here, and we're going to start with some calculations on this now. We have to do some calculations on this, understand how to manipulate these formulas and how to also find capacitance in series and parallel. Oh, and energy stored by a capacitor. All right. Okay, so nice. Copy it down. When you finish, feel free to log out. I'll see you all next week, please. All right. Okay, only first. Yeah. Lab phone not in there, Bradley. All right, I want to check and see. All right, I'll look for it. Try and do up these, and I'll bring you all in the following week to do up some more. All right, so that is charging and discharging. You have to be able to draw it, describe how it happens, and sketchy graphs and write the formula. Right, Brian? When you come next week, test on that. Capacitance. Just do you alone again, a test.